Well, hello, A&P class. I wanted to try a little bit of a different way to record today, just to see if it was helpful, to get to see my face as I'm talking, along with the screen and what I'm writing on the iPad. So we're going to try it that way, and send me your feedback. Think this is better, worse? I'd love to know. Just trying all this stuff out and seeing what works best. So let's get started. So today we're talking about gas exchange and oxygen transport. It's a short set of notes here, only 11 slides. So I may go ahead and record the one for Wednesday here today as well and just post them both at the same time. We'll see. All right, let's get going. So when we talked about those different functions or processes of respiration and processes of the ventilatory system, the respiratory system, one of those was external respiration, right? And external respiration means moving oxygen from the air in the lungs onto the hemoglobin in the red blood cell, right? So in order to do that, we must have what's known as a concentration difference, okay? And again, just like it was when we were moving air from the atmosphere down to the alveoli, we had a concentration or pressure difference, okay? And really we can use those two terms interchangeably, concentration or pressure in this setting. We're talking about gases because when we measure the concentration of a gas, we use the partial pressure of it. Okay, so we're going to be using partial pressures the whole time to talk about the concentration of oxygen or CO2 or either of those gases. Okay, so the idea here, we must be going from a concentration of higher to lower. All right, and that's what has to happen. So when we breathe air in, that fresh air that's coming in comes down to our alveoli, right? So this has a lot of oxygen. This has a lot of oxygen. This doesn't have as much right here in the capillary. This is zooming in on the capillary, right? So high oxygen here. We have lower oxygen in here, right? So it's going to move from higher to lower. And that's just the opposite with CO2, right? We've got high CO2 in the blood. We've got low CO2 in the alveoli. So CO2 is going to move that direction, right? And that's the gas exchange that happens. That's the external respiration. Okay, so let's talk about just exactly how we measure that concentration. I said it's going to be in terms of pressure. It's in something that we call partial pressure. And that partial pressure is something that we're actually going to, you're going to have to know how to calculate, okay? I will give you some of the information you need, but you will need to memorize some of the information. The main thing I want you to memorize is this, okay? So this is the percentage of oxygen in the air in our atmosphere. If you want to remember it as 21, that's fine. 20.9, 21, that's fine. The questions on the exams, I'll give you a little range that is correct, and so 21 will be just fine, okay? So normally we have about 70, a little over 78% nitrogen, a little under 21% CO2 or oxygen, and then just a tiny bit of CO2, 0.04%, okay? Now those fluctuate a tiny bit, but they're always something like that, okay? So when we look at a sea level condition, like at Point Loma, okay, right at the ocean, pretty much, right? A normal atmospheric pressure, and this is total atmospheric pressure, is about 760 millimeters of mercury. Okay, so we're thinking 760 millimeters of mercury. When we think of atmospheric pressure, you think of all of the weight of the air on top of your head. Okay, so all the space between your head and the top of the atmosphere. Okay, there's a bunch of air particles between your head and the top of the atmosphere. The further you are away from the top of the atmosphere, the more pressure you have on your head, right? So when we compare sea level of 760 millimeters of mercury, is just the unit that's used for that, to Mount Everest, the tallest place on Earth, right? We got way less air on top of our head if we're on top of Mount Everest, right? Because we're way closer to the top of the atmosphere, okay? So that total atmospheric pressure is much, much lower. It's only 253 compared to the 760 that we had here. Okay, so then the way that we calculate partial pressure, and really what that means, partial pressure means that of that total pressure we have, of that 760, we can divvy that up to the contribution of each of the gases in the air, right? We know that nitrogen doesn't account for all of that weight on top of us, and oxygen doesn't, and CO2 definitely doesn't, okay? Each of them account for a little bit. And so we do that by a simple equation of just taking our total atmospheric pressure and multiplying that by our percentage, okay? So we take that 78.6%, we put it back in its decimal form, which would just be moving that decimal place to the left, 2, right? That's back in its decimal form. So 760 times 78, or times 0.786, that will give us the partial pressure of nitrogen at sea level, right? So that's that one, okay? We do the same thing for oxygen. We use our 760 again, times that by 0.209. We take our CO2, take our 760 again, times that by 0.0004, okay? And that's how we do it. So the only thing that's gonna change when we do this at the top of Mount Everest is the 760, right? So instead of the 760, we use our 253. So for nitrogen, we're doing 253 times 0.786. Okay, oxygen, we're doing our 253 times 0.209. CO2, we're doing our 253 times 0.0004. Okay, and you do those calculations. So what I recommend is go ahead and stop or pause your YouTube video for a second, do those calculations on your own, and then I'll uncover them and see how you did. Okay, so we see nitrogen, 760 times 0.786 gives us 597.36. Oxygen, we get right about 159-ish, and CO2, we get 0.3, okay? Now, if we went ahead and added those up, we should get our 760, right? And we do. If we add those three up, we get 760. And so we can always double check our math in this case, at least in the way that I'll set up the problems for you. Of course, this isn't perfectly how it always is, but this is the way I'll set up the problems for you. So it does, the gases I give you do get you to the total atmospheric pressure. Okay, what about at the top of Everest? Take that 253 times 0.786, we get 198.86, CO2 about 53, or sorry, oxygen about 53, and CO2 about 0.1. And there we have it. So that's how you calculate partial pressure. Again, you need to memorize this. You need to memorize that percentage of oxygen. Okay, I'll give you everything else you need. I'm not going to give you equations, but I'll give you everything else you need as far as I'll give you the total atmospheric pressure. And that's really all you need to calculate partial pressure of oxygen. You will not need to memorize the percentage of CO2 and the percentage of nitrogen. Okay, all right, so when we look at this gas movement with a gradient, then we're talking about, just like I said before, we must have a pressure difference for a gas to diffuse from one place to another, okay? And so when we look at this figure over here on the right, we have the alveolus, an alveoli there, okay? And then we down here is where we're at the tissues, where the cells are, where we're sending that oxygen, right? And then right in the middle is the heart. Okay, so oxygen or blood is coming back from the tissues to the right side of the heart, right? Then it's getting pumped to the lungs. We see there that it has a low amount of oxygen, right? Only 40 millimeters of mercury. But in the alveoli, we've got 104. Okay, so we've got a big pressure difference. That oxygen is going to go that way. For CO2, it's the opposite. We've got a higher amount of oxygen than we do in the alveoli. So that oxygen, or that CO2 is going to go that direction into the lungs. Okay, by the time we get over to the arterial side, after we've gone through the capillaries in the lungs, now we got an equal amount of oxygen, equal amount of CO2. So no more gases moving at that point. Now that blood gets sent to the heart, gets pumped out of the aorta, goes back. Now we got some more pressure differences here, right? Our CO2 there is lower in the blood than it is in that interstitial space of the tissues, right? So that's going to push CO2 into the blood. And now it looks like we've lost a little bit of oxygen, just getting down, which is normal, getting down to the tissues. And then we see we still got a lot more oxygen in the blood than we do in the tissues, right? So that's going to move oxygen into the tissues, into the cells, so the cells can use it. And then look, all the way down in the cells, it's even lower. That's good because we need it to move from the interstitial space into the cells again. So we need another drop down in that concentration of oxygen for it to move. Okay. And so one question there, why is alveolar O2 pressure lower than the atmospheric pressure, right? This is 104, okay? And you can see the inspired air is 160, okay? So what happens to it as it goes down, right? Well, think of residual volume, right? Remember that residual volume, the air that doesn't leave the lungs? That is kind of stale air. That's air that's already had the O2 extracted from it. And so when that new air comes down, it has to mix with that residual volume, and then that lowers the amount of oxygen in the air. Okay, so mix with old air. Okay, so then know in which locations O2 and CO2 move in each direction, and you see that right there, right? Yeah, so you see that. And then what about at altitude? Well, what happens at altitude if we change this 160 of the inspired air? Let's go back to the last slide. We change that inspired air from 160, which was this one pretty much, right? Change that down to 52, right? So what happens? Now this is 52 instead. So that means we're going to drop this one probably down to 45, right? If this one's only 40, we could still move a little bit of air, but not much, right? So really, this one's going to have to go lower than 40. It's going to have to go into the 20s in order to move some oxygen. But what does that mean? The tissues, O2 was 20 before. It can't stay that, and we won't move any oxygen. So the tissue is going to have to drop way down to 5 or something, so we can just move air. So the end result is less oxygen in cells, right? We have to get less oxygen in cells just to be able to move it. All right, so let's kind of summarize this here. Where is the partial pressure of CO2 the highest? Okay, would it be in our systemic arteries, systemic veins, pulmonary artery, or pulmonary vein? Okay, when we look back at this, you can see there we have pulmonary veins, pulmonary artery, systemic artery, systemic veins. So when we're bringing that gas or that blood back that is full of CO2, as full as it's going to get, that has to be right after the tissues, right? It has to be right after we have just filled it up with CO2. So the highest level of CO2 is definitely going to be on the venous side, right? Because that's where we're putting CO2 in, right? So if we look at that, systemic artery, systemic veins, pulmonary artery, pulmonary vein, okay? So the pulmonary vein, that's the one that's bringing blood back to the heart, right? Pulmonary artery is the one that's sending blood from the heart to the lungs, and so that's got to be the right answer, right? Because that's already received all of the deoxygenated blood from everywhere, right? It's received all of it, and now it's all collected back to the heart, okay? And that's right before it gets filled up. Okay, a few other questions here. Where does CO2 enter the blood? It enters at the tissues, right? Oops, excuse me. Oops, sorry about that. Clicked on that notification, didn't mean to. Where does CO2 leave the blood? In the lungs, right? It gets sent up to the lungs, and then it leaves the blood, goes into the alveoli. Where does oxygen enter the blood? In the lungs. Where does oxygen leave the blood? At the tissues. Okay, so it's kind of the opposite for those two. Okay, so let's talk a little bit about how oxygen is transported. All right, so 98.5% of oxygen is carried by hemoglobin, right? So those proteins inside of our red blood cells, almost all of it's carried right there. So very, very efficient, okay? Very efficient carrying system for oxygen in the body. And that other 1.5% is just dissolved in the plasma, not much, okay? What about CO2? CO2 is a little bit different. About 70% of it is carried in the form of this. What's this? It's the bicarbonate ion, right? That's bicarbonate. That's that buffering system that we talked about. We'll talk more about the bicarbonate buffering system next time, okay? And then 20% actually sticks onto hemoglobin in a similar fashion that oxygen does, but just a little bit different. And then 10% of it gets dissolved in the plasma, just like the 1.5% of the oxygen, okay? This is the equation for the bicarbonate buffering system. Okay, so we take, and this can go either way, right? This is a reversible reaction. Okay, so if we're producing CO2 down at the tissues, then we're going to flip this equation this way, right? That CO2 is going to bind with water, create carbonic acid, and then create bicarbonate and hydrogen, right? And so this is how we're carrying that CO2 in that example. And this is that 70% of CO2 being carried that way. Okay, so let's talk a little bit about this this concept here that's known as the oxyhemoglobin dissociation curve. Okay, so the oxyhemoglobin dissociation curve is really just a plotting of the relationship between the partial pressure of oxygen in the blood, okay, and that's on the x-axis here, okay, and it's plotting that against the percentage of oxygen saturation in the hemoglobin, and that's on the y-axis here. Okay, so if we're up here at 100%, that means all of the hemoglobin has oxygen on it, right? It's 100% full. Okay, if we're down here at about 75%, that means 75% of the hemoglobin is full of oxygen. If we're way down here at 25%, that means only 1 in 4 of the hemoglobin actually is full of oxygen. Okay, and so you can see that this relationship, or how full the oxygen gets, is totally dependent on the concentration or the pressure of oxygen, right? The more oxygen that there is around the red blood cell, then the more oxygen flows in, right? This makes sense. This is what we've just been talking about. The higher the partial pressure of oxygen around the red blood cell, the stronger relationship we have of moving oxygen into the red blood cell, because we're going from higher to lower concentration. So then the more of it gets in the red blood cell. But then as we move down this, the lower partial pressure of oxygen means that the less oxygen moves in, and the less oxygen we actually get in the red blood cell. Okay, so let's talk about that a little bit. Okay, so when we look at this curve, it's got a few features that are really good to point out and good to think about. Okay, so where in the body and in the curve is the plateau? Okay, a flat part of that curve, where is that? Okay, why would that be beneficial? And then number two section here, number two question is, where is the steep part of that curve? Okay, where is it steep? Where is it going straight up and down? Plateau would be, where is it flat? Steep part is, where is it going straight up and down? Okay, and why would that be beneficial? And then lastly, why would altitude be a problem? So I'd encourage you to go ahead and click pause on the video, think about these questions for a second, look at those graphs right next to you, and see if you can answer them. Okay, so hopefully you took a second to do that. So where in the body is the curve, or end on the curve is a plateau? Okay, so this is the plateau part. This is up here. It's pretty flat up there, right? So the very high part, okay? So it's the right side, okay? And then when we think about where in the body this is occurring, what we have to think about is, where in the body do we see partial pressures that look something like that of oxygen, right? Somewhere between 70 and 100. Where would we see that? Well, let's go back. We'll go back and see that right here. Take just a sec. Okay, where do we see partial pressures of oxygen around 100? Look at, in the alveoli, it's 104. Okay, once we're here on the artery side, 95. So we're right around 100 there. Okay, and then the other one you'll want to point out, you want to see, is this one, partial pressures of oxygen around 40. That's in the interstitial space. Okay, let me go back to where we were. Okay, so we see on the right side of the lungs. Okay, so what that means is the partial pressure that we typically see in the air, partial pressure of oxygen that we typically see in the air at the that's around 80 to 100, that partial pressure that would fill up our oxygen or fill up our hemoglobin almost to 100%, that's the normal partial pressure we see at the lungs. So that's perfect, right? That's a perfect relationship for the air that we happen to be breathing, right? So normally we can fully saturate our blood, okay? This is that little thing that you get at the doctor's, and they put that little pincher thing on your finger. It's got that red light. That's the saturation measurement system. That's measuring this exactly. Most of the time it's 98, 99, 100% saturated. It's because your partial pressure of oxygen is around 100, okay? And then if we go down, or so why is that beneficial? Well, because it stays saturated, okay? So if we're normally right around here around 100, but then what if for some reason we get into some room where there's really bad ventilation and the oxygen levels are a little bit lower? Well, maybe they drop to 70 partial millimeters of mercury instead of 100. That the oxygen actually gets in our lungs, okay? Well, where do we get saturated at 70? Still pretty much 95%, right? All the way from 100 to 70, as far as partial pressure goes, that only changes our saturation by about 5%. That's incredible, right? That's a wonderful part of this curve, is this nice plateau, because this helps us to stay saturated over a large range of pressures that would be normal pressures that our body would be under, partial pressures of oxygen, okay? And so then this also allows us to load oxygen easier, okay? So number 2 question there, where's the steep part, right? So the steep part is the left side, right? We see it right here. The steep part, that curve is dropping pretty much straight down, okay? And so why is this beneficial? Well, this is beneficial because number 1, it makes it easier to drop off oxygen, right? So the partial pressure that we saw at the tissues, excuse me, sorry. Partial pressure we saw at the tissues was 40, right? So that partial pressure of 40, that gives us a saturation of about 75. So that means about 25% of that oxygen that's on the hemoglobin will get dropped off in a normal situation, okay? But then let's say we start exercising, right? We start exercising and we start using up that oxygen that's in our tissues, okay? So instead of the oxygen saturate, or instead of the concentration of oxygen in our interstitial space going from 40, this will be at rest. We start exercising, we start using up that oxygen, right? So that oxygen is going to drop. Maybe it drops to 20, okay, during exercise. Okay, so now that red blood cell finds itself in a situation where there's only 20 millimeters of mercury around it. Okay, so now we're here instead, right? So we went from being 75% saturated all the way down to being 25% saturated. So just from going from 40 millimeters of mercury down to 20, we dropped off 50% more oxygen, right? And that's a great part about that curve, right? It's easier to drop off oxygen. All we have to do is change that partial pressure just a little bit, right? Change that partial pressure just a little bit to the left if we're at the steep part, and we're going to drop off a lot more oxygen. Whereas when we're up at the plateau, we change that partial pressure a little bit, and it doesn't change the saturation at all. We still get fully saturated, but down there at the tissues, we change that partial pressure a little bit and we drop off a lot more. That's helpful, right? That's what this curve is all about. Okay, so why is altitude a problem? Altitude is a problem. I should be coming back here in a sec. There we go. Altitude is a problem because, sorry, keep doing that. More try. So altitude is a problem because these change, right? And what happens there when these change is instead of coming in at 100 here, when we looked at the partial pressure at the top of Mount Everest, it was only 50 at the alveoli, right? So we were right here, okay? So then we only saturate up to about 80%, okay? And then that's just going to be much lower. So the altitude almost moves us out of that plateau region. In some cases, high altitude can move us out of that plateau region. And so then we don't fill it up as well as we could. We'll talk a little bit more about oxygen, or about altitude soon. Okay, and this one is not showing up correctly. This graph is kind of messing us up, but I'll go ahead and just draw it here. Okay, so we have this same curve. Okay, got the same situation. We've got our steep part of the curve, and we've got our plateau part. Obviously, it doesn't look just like that, but this was like 100 millimeters of mercury. Okay, this one was 40, about there. Right, this was 100% saturated. Okay, let's go back and just see. The normal 40 would get you to about, sorry, let me go back and just see, get you to about 75. So we'll do that. Say that normal gets you to about 75. Okay. And so, yeah, so normally when we're up at 100 millimeters of mercury, we're at 100%. Normally when we're at 40 millimeters of mercury, we're at about 75%. Okay. But the thing is, we can move this curve. We can actually shift it. Okay. And I think what I can do here is actually change the color so it can match what it says. So we're actually going to make the, yeah. Okay, so we're going to make the red line is going to be, so no shift is red, okay, and then leftward shift is going to be black, and then we'll get the blue in there, okay? So no shift is red, just because I'm drawing it, it's a little bit different than the way I had it on the slide. It's not coming up right on my iPad for some reason. So let's look at a leftward shift, okay? If all of a sudden we're able to shift this curve to the left, so it's the same curve, right? But it looks something like this instead. Okay, so if we shift that curve to the left, what does that mean? What does that mean for our saturation? And we'll use that partial pressure of 40. Okay, so we go from 40. Yeah, so we go from 40 and we go up. Right before we were at 75 there. Now we're what? Now we're closer to about 90%. Okay, so that leftward shift actually caused more loading. Right, so with each shift, state whether it makes O2 unloading happen more or less. So unloading with a leftward shift would be, unloading would be less, right? Less unloading, but more loading. Okay, we'll talk about a leftward shift when we talk about altitude a little bit more, but for now, that's the way we'll look at it. Less unloading, more loading. Okay, but now I'm going to change my color here to blue. Okay, so now we got blue line is a rightward shift. Okay, so we're going to do something like this. Okay, so that rightward shift now. So now we're moving from red, which is normal. Blue is a rightward shift. So what do we see now for 40 millimeters of mercury? 40 millimeters of mercury here. We go over to about 25% saturated. Okay, and so yeah, let me go ahead and put my color back. And so how does each shift affect O2 saturation? So the rightward shift lowers it, right? It went from 75% down to 25% at 40. And the leftward shift increased it, went from 75% up to 90%. Okay, so with each, so with the rightward shift, we have more unloading. More unloading and less loading, right? Because at 100, we have only about 75%. So we don't saturate as much, but when then that blood gets down to the tissues, we actually drop off a lot more, right? And why is that? Well, how do we get these curves to shift? Okay, so causes shift. Okay, so the causes of the shift are shown here. There's really three causes. One of the causes has to do with temperature, the other one has to do with hydrogen ion concentration, and the third one has to do with CO2 levels. Okay, so now the easiest way I think to think about these things is this. All three of these things are related to metabolism, right? The more metabolism we do, the hotter we get, right? The more we're burning energy, the hotter we get. Okay, so as metabolism increases, temperature increases, right? Because we're breaking down energy. A lot of that energy is lost as heat. Okay, what about hydrogen ion concentration? That increases too, right? Because that's using the glycolytic system, producing that lactic acid, making that, right? So as metabolism increases, hydrogen concentration increases, or we could say pH decreases. okay? And then CO2, right? As metabolism increases, CO2 increases because that's the byproduct of the Krebs cycle, part of the higher parts of metabolism, right? CO2 is a byproduct. Okay, so why does that happen that way? Well, look at the image here. This is showing a red blood cell. It's showing as temperature increases, more oxygen comes off, right? So that would be causing the leftward shift, okay? And that has to do with the shape of the hemoglobin protein. The hotter that protein is, it starts unfolding. It's not its ideal temperature anymore, and it starts to unfold, so it doesn't hold on to oxygen as well, and it lets it go. Okay, same thing with hydrogen. Hydrogen's a little bit different, but those hydrogen ions come and they bind to the hemoglobin, which again changes the hemoglobin shape, makes it so that hemoglobin is more, it just doesn't have the right shape to hold on to oxygen, so it lets the oxygen go. Okay, same thing with CO2. CO2 comes out of the tissues, binds to hemoglobin, and that is going to cause the hemoglobin to change shape and release oxygen. Okay, so all those things, high temperature, high CO2, high hydrogen, all of these things cause a rightward shift. Okay, and so why would we see these three changes? Because of that increased metabolism. Okay, and so all these cause a rightward shift, and just the opposite, right? If we have decreased temp, decreased hydrogen, or decreased CO2, then we get a leftward shift. All right, so let's think about this a little bit more. So what does a rightward shift mean for loading of oxygen? Okay, rightward shift means, remember, we're sending that curve to the right. So loading is going to go down, going to be less loading, but for unloading, that's one we already talked about, that's going to make unloading go up. Where do we typically see this? We would typically see a situation that has high CO2, high hydrogen, high temperature. We'd see that down at the tissues because that's where all the metabolism is happening, right? But then a leftward shift would do the opposite, right? A leftward shift would increase loading of oxygen, decrease unloading. And where would we typically see situations where we have low CO2, low hydrogen, and low temperature? We typically see that at the lungs. So that would be helpful, right? Because then we would be able to load more oxygen. It'd be helpful at the tissues to increase unloading because that's where we're trying to drop off oxygen. All right, guys, we're done there. Hopefully this works out. Give me some feedback on this new method, and we'll see you guys soon.